Welcome to the lecture series on atomic spectra. In the last video, we've derived an expression for the quantization of radius. In this video, we are going to first derive the expression for quantization of energy, and then we'll use the idea of energy quantization to prove this expression for wave number right here. So how could we represent the total energy of electron that is orbiting in some nth orbit? The energy in nth orbit equals the sum of kinetic energy plus potential energy in that orbit. How do we write kinetic energy? It is simply half mv square. How do we write potential energy? या तो हमें directly पता हो कि potential energy is negative ke square over r. This has to be Rn, that is radius of nth orbit, and because velocity depends on the orbit the electron is revolving in, so we should be writing Vn here, right? अगर इसकी आप working देखना चाहते हैं तो let's just do it here. We've seen force in this case, that is Coulomb's force, is represented with K, product of magnitude of charges on both the bodies, that in our case charge on nucleus and the charge on electron. Electron पर तो charge का magnitude क्या है? It is 1.6 exponent minus 19. What is the magnitude of charge on nucleus? We are dealing with hydrogen atom, and hydrogen atom के nucleus में there is only one proton, right? And the charge on proton exactly equals the charge on electron in magnitude. बस nature opposite होती है, right? Divided by the square of separation between these two charged bodies, and this separation is orbital radius for nth orbit, right? So this becomes k e square over r n square. Abhi tak this is the formula for force, but we are to write the formula for potential energy. We know that force is the gradient of potential energy. In other words, we can write that potential energy is the integral of force. Here, with respect to this separation r, because baki dono values are constant. So we can write potential energy equals k e square over r n square. Let's just take these constants out of this integral. This becomes k e square integral of 1 over r n square. Then we'll move this rn square to the numerator. This becomes rn raised to the power minus 2. How do we take derivative? How do we take integral, right? So we'll just add 1 to this power, that is rn minus 2 plus 1, and then we'll divide this expression with the resultant power, which in this case is minus 2 plus 1. So we can write k e square with this rn raised to the power minus 1 over this minus 1 here. And finally, we could write it as k e square, this negative here, and this rn raised to the power minus 1 goes to the denominator and becomes rn simply. This right here is the expression for potential energy, which we have written directly here, right? And you can write it directly यहाँ पर भी, depending on the marks जिसके लिए examiner is asking you to derive this question. Now that we know the expression for kinetic energy and potential energy, all we have to do is to simplify this expression and then rewrite this equation. We'll write En equals half mvn square minus ke square over rn. We can also rewrite this expression using the idea that when we consider the electron revolving around the nucleus in a specific orbit, then Coulomb's force plays the role of centripetal force. So we can write F centripetal equals F Coulombs. How do we write centripetal force? It is mv square over r, rn in this case, right? Because हम general equation derive कर रहे हैं अभी. How do we write Coulomb's force? I just mentioned here that it is k e square over rn square. Let's just calculate the value of velocity from this expression. Okay, let's just do this one thing. We have this half mvn square here, right? So let's just directly find the value of half mv square from this expression and then replace it in this equation. This Rn here gets cancelled with this Rn and we get mv square equals k e square over Rn, right? And we can see that सिर्फ एक half missing है यहाँ पर, right? So we'll multiply this side of equation with half to get half mv square. And in order to balance what we did on the left side, we have to multiply this equation with half as well, right? So we get this equation here. Now we are going to replace this value in this equation. Okay, so we get En equals k e square over 2Rn in replacement of half mv square with this minus k e square over Rn as it is, right? Now we can just simplify this equation. It becomes negative k e square over Rn. With this 2 in the denominator, just consider it as half minus 1, right? While keeping this k e square over Rn is common. Okay? So you will get minus k e square over 2Rn. This is the expression for energy in nth orbit. But in the last lecture, we've already calculated the expression for radius in nth orbit, right? So we'll just put in this radius here and then we'll get the expression for quantized energy. Recalling the results for this nth orbital separation from the last derivation, Rn equals n square, that is principal quantum number, h square, that is Planck's constant, and then we have 4 pi square k, mass of electron, charge on electron, and then a square, right? This is the expression for orbital radius. We are going to place this r in this equation. This becomes En equals minus k e square over 2 times this radius, which is n square h square over 4 pi square k m e square. 2 ones are 2, 2 twos are 4, right? And then this numerator gets multiplied with this denominator gets multiplied with, so we get minus k e square with this factor right here, which is 2 pi square k m e square, and then there's n square h square in the denominator. We can rewrite this equation as minus 2 pi square k square m e raised to the power 4 over n square h square. It is obvious from this expression right here that this 2 is constant, this pi is constant, this k is constant, mass of electron, charge on electron, Planck's quantum number, Planck's constant, all of them are constant except this n square here, right? So we'll just put in these constants in the calculator to get the value of these constant, and then we can reduce this expression as En equals negative the value of this collective constant divided by this n square in the numerator. When you put in these values in calculator, you'll get 13.6, keeping in mind that you are to put in the value in joules, right? So what is this? This is the expression for quantization of energy. This expression right here suggests that if you are to calculate the energy of electron that is in first orbit, you will place n equals 1, that is E1 equals minus 13.6 over 1 square. If you are to calculate the energy of electron that is orbiting in second energy level, you will place n equals 2, that is E2 equals minus 13.6 over 2 square, right? And keep this thing in mind, ये जो आपके पास यहाँ पर final answer आ रहा है, it is in electron volts, right? So here we get minus 13.6 electron volt. Simplify this equation and you'll get minus 3.4 electron volts. Likewise, E3 is minus 13.6 over 3 square, and this becomes minus 1.51 electron volt and so on, right? इसका मतलब energy की भी सारी continuous values नहीं allowed. Specific values of energy are allowed depending on ऑर्बिटल रेडियस क्या था. So this expression right here suggests कि सिर्फ रेडियस नहीं, एनर्जी भी क्वांटाइज्ड है. And now that we've seen that this minus 13.6 electron volt is the energy of electron in first orbit, that is the ground level. So we can also rewrite this equation as En equals negative of energy in the first orbit, which we could represent with E1 here. लेकिन एक आध बुक्स में इसको E नॉट से भी रिप्रेजेंट करते हैं, राइट. तो आपको बस पता होना चाहिए कि ये किस चीज को रिप्रेजेंट कर रहा है. And then this n square in the denominator. Now we are going to use this final result here to derive the expression for wave number. अच्छा, keep this thing in mind. This derivation is being asked for different mark distributions. Like if they are asking you to derive this expression for like 5 6 numbers, तो फिर आप वो start से जो हमने working start की वो करेंगे. लेकिन if they ask you to derive this for like 3 numbers as they do in Aga Khan board, तो फिर you are supposed to start this equation from this point, right? Now what we are going to do is we are going to consider an electron in higher energy level, and this electron is to transition to some lower energy level, right? Let's just say that the higher energy level is level for suppose n, and the electron is making transition to some lower energy level p. So we'd say that the energy in this higher energy level would be represented with En equals minus E1 over n square, and this electron is making transition to some lower energy level, so the energy in this lower level P would be represented as Ep equals minus E1 over P square, right? How can we write the difference of the energy? Because as per the Niels Bohr theory, the third postulate of this theory, we've seen जब भी electron higher level से lower level में transition देगा, तो it will emit the photon of energy that equals the difference between the energies of the levels involved in the transition. So we'll say जो photon energy emit करेगा, जिसकी अपनी value would be hf, this equals the difference of energy. How do we write difference of energy? We have En here minus EP here, right? Because इस level से इस level में उसने transition दी थी. And because we are to derive this expression in terms of wavelength, तो इस frequency को पहले wavelength में convert कर लेते हैं. We have seen that we can replace this frequency with c over lambda, right? So we'll write c over lambda here, following that v equals f lambda. इस case में speed of light, right? Because radiation travels with this speed. So we can write f equals c over lambda. So we've replaced this frequency here. We will replace these energies here. This becomes minus E1 over n square. This minus from formula, and then this becomes minus E1 over p square. Let's just rewrite this equation. We get hc over lambda equals, taking this E1 common here, we get minus 1 and minus minus plus 1 here, right? We'll write minus 1 over n square minus minus plus 1 over p square. एंड ज़रा इसको सिंप्लीफाई कर लेते हैं, बल्कि रीअरेंज कर लेते हैं थोड़ा सा. विल कीप दिस 1 ओवर लैम्डा हियर, बिकॉज हमें पता है जो हमें डिराइव करना है उसमें दिस 1 ओवर लैम्डा इज द सब्जेक्ट ऑफ आवर इक्वेशन, दैट इज द इनवर्स ऑफ वेवलेंथ, जिसे हम वेव नंबर भी कहते हैं, राइट? बाकी दिस एच सी could be shifted to the right side of the equation. This becomes E1 तो already इधर था. This HC comes here in the denominator to the right side, and then we have this expression here. इसको बस हम अपनी आसानी के लिए rearrange करके कैसे लिख सकते हैं? Since this term is positive, तो पहले इसको लिख देते हैं. We have 1 over p square, and then this minus 1 over n square. बस आपको पता होना चाहिए कि this n was the higher energy level and this p was the lower energy level जिसमें transition के बाद आया है electron, right? वैसे तो this would have worked, लेकिन मुझे पता है this E1 is constant, right? minus 13.6, and then मुझे पता है this Planck's constant is constant and this speed of light is also constant, right? So हम directly इन तीनों की भी values place करके जो resultant constant है उसे यहाँ पर लिख लेते हैं. This becomes 1 over lambda. Energy in ground state is 13.6 over this h 6.63 exponent minus 34, and there's a speed of light 3 exponent 8 here. But do not forget कि ये जो हमारे पास एनर्जी है ये इलेक्ट्रॉन वोल्ट में, राइट? जबकि जो h का यूनिट है यहाँ पर इट इज जूल्स इनटू सेकंड. जूल्स और इलेक्ट्रॉन वोल्ट दोनों एनर्जी के यूनिट है. एक टाइम पे हम दोनों को नहीं यूज कर सकते, राइट? सो वी हैव दिस स्टैंडर्ड यूनिट joules wala here, so we are to convert this energy into joules as well. And we have seen जब भी हमारे पास एनर्जी इन जूल्स चाहिए होती है तो हम क्या करते हैं, इलेक्ट्रॉन वोल्ट वाली एनर्जी को मल्टीप्लाई कर देते हैं विद द चार्ज ऑन इलेक्ट्रॉन, दैट इज 1.6 exponent minus 19. This right here is the energy in electron volt. We'll multiply it with 1.6 exponent minus 19 to get the energy in the unit of joules, right? And this factor 1 over p square minus 1 over n square right here. This is going to give you 6.83 exponent 25, but multiplying it with this number will give you 10940170, and then this 1 over p square minus 1 over n square as it is. Isko we can also write as, of course, 1.094 exponent 7, and this number is nothing but Rydberg constant that we represent with RH, right? So this becomes RH into 1 over p square minus 1 over n square. Now, how do they ask such questions in exam? Numerical problem के तौर पे वो आपको कोई भी दो levels बता देंगे जिसके दरमियान इलेक्ट्रॉन ने transition दी है, and then they'll ask you to calculate the wavelength of this transition, right? How can we do so? पहले consider कर लेते कोई भी transition. Let's consider बार्मर सीरीज की कोई ट्रांजिशन कंसिडर करते हैं. इलेक्ट्रॉन ने थर्ड एनर्जी लेवल से सेकंड में ट्रांजिशन दी है. we've agreed कि n represents the higher energy level, right? So third से second में उसने transition दी है, so we'll say n equals 3 and this p equals 2 because this p represents lower energy level, right? So just place this value in this equation. This becomes 1 over lambda equals Rydberg constant, which is 1.097 exponent 7, and there's 1 over lower level ka square, that is 2 square, minus 1 over higher level ka square, that is 3 square. This becomes 1 over lambda equals 1.097 exponent 7, 1 over 4 minus 1 over 9 here. Put in this value in calculator and you'll get 1519468, right? And since we are to calculate the wavelength, this is the inverse of wavelength, so we'll just reciprocate this equation. Wavelength becomes 1 over this value right here, 1519468, and this gives you 6.58 exponent minus 7 meters. In other words, 658 nanometers. And हमें पता है this 658 lies in visible region because visible region 400 nanometer से 700 nanometer तक expand करता है, right? और हम पीछे स्पेक्ट्रल सीरीज में देख भी चुके हैं कि बामर सीरीज में जो हमारे पास स्पेक्ट्रल लाइन आती है वो विजिबल रीजन में फॉल करती हैं. इसका मतलब है दिस राइट हियर इज द करेक्ट आंसर टू दिस क्वेश्चन. इन डेरिवेशन में बस एक कंफ्यूजन इसकी होती है, बच्चे इसे एंड में रेसिप्रोकेट करना भूल जाते हैं. या फिर जो दूसरी कंफ्यूजन हो सकती है वो इस एनर्जी लेवल में. तो आपको पता होना चाहिए पहले आप लोअर एनर्जी लेवल को स्क्वायर करेंगे एंड देन आप हायर एनर्जी लेवल की वैल्यू को स्क्वायर करेंगे. This is all from this lecture. Let's end this here. In next video, we'll discuss the production of X-ray. Till then, Allah Hafiz.